All right, so the way we want to start this out is kind of, get a visualization of it here. Okay, so we got a toboggan racing down a hill. So there's the toboggan. Okay, and at one point it's 30 meters above the bottom. Oh, and my board is out of whack again. Okay, and moving at 14 meters per second. Okay, so we've got this initial position and this initial speed, okay? And then it says a little while later, it's moving at 23 meters per second. How far above the bottom is it at this point? So, meaning it's down here and its speed is 23 meters per second, we're looking for the final height, okay? Here's what we know. We know the mechanical energy at the initial point and the final point are the same. They're equal, okay? It's a law of conservation of energy problem. All right, so we start out with this. The mechanical energy initial equals the mechanical energy final. How do we calculate mechanical energy? Right, potential plus kinetic. All right, so I go EP initial plus EK initial equals EP final plus EK final. Looking at this question, are any of those zero? Not likely. Okay, I mean, we know for sure that the initial potential is not zero. We know for sure the initial kinetic is not zero. We know there's final kinetic, and they're asking us what the height is. We would have to assume they're not going to make us calculate a number that would be zero, so we'd have to assume all of those energies have an actual numeric value, thus we can't cancel any of them. So what we're looking for is part of this. Okay, it's part of our final potential. Right, the final height would be in there, m times g times hf. Okay, so how do I get EPF by itself right now? Right, subtract EKF over to the other side. All right, so I'm going to have EP initial plus EK initial minus EK final equals EP initial. Everyone following me so far? Okay, so now I want to expand this out so that my formulas are all in there. All right, so here's my initial potential, here's my initial kinetic, subtract my final kinetic equals my final potential. Okay, what did the question not give you? Do you need it? No. All right, and if it doesn't give it to you and you don't like that, pick a number. It won't make any difference. Okay. All right, so I'm going to cancel off all the masses. One less thing to move around. I want HF by itself. What do I have to do with G? Right, divide it over to the other side, because right now I'm multiplying. My rules of algebra say if you want to move something, do the opposite. All right, so there's my formula. I'm now solving for HF. Okay, I've essentially got my initial potential plus my initial kinetic minus my final kinetic divided by G gives me my final height. All right, so we got to plug in all of our numbers here. So that'll be 9.81 times 30 meters, the initial height, plus 1/2 times 14 squared, the initial speed, minus 1/2 times 23 squared, the final speed, divided by 9.81. That will give me my final height. Okay, so we got 9.81 times 30 plus 0.5 times 14 squared minus 0.5 times 23 squared divided by 9.81. Okay, so when it's moving at 23 meters per second, it's 13 meters above the ground. Okay, or above the bottom of the hill, we would say. Okay, everybody kind of follow what I did there? The nice thing about conservation of energy problems is they all work the same way. Just like work energy theorem problems all kind of work the same way. Okay, you're always going to set it up like this. EI equals EF. Then you'll write out the energies. Then you'll isolate the energy type that contains what you're looking for, and then you'll put in the formulas, manipulate, and solve. Okay, it's always going to be the same things. At first, the algebra looks a bit intimidating because there's a lot of stuff in there that's got to get moved around. But once you get the hang of it, it's always going to be the same stuff. Okay. Any other questions on what we did there? Yep. Okay. It gets canceled out because because we're assuming this is an isolated system. So there's no forces acting other than gravity. And since gravity acts on all things equally, regardless of their mass, the speed or the height are not dependent on how big something is. Okay? If I drop a piano and a feather in a vacuum, we saw that video, right, where they drop the big ball, they accelerate to the same speed regardless of their mass. Well, the same is true here. Because we're always dealing with an isolated system, the mass doesn't affect how fast the object goes. Okay? Now, it does affect the amount of energy that the object would have when it gets there. So if I'm being asked to calculate the energy something has, I can't cancel the mass then, because kilogram is part of joules. Okay? But if it's just asking me to calculate a speed or a height, those are independent of mass. Okay? That sort of makes sense? All right. Try this one. Car drives off a cliff at 25 meters per second. Okay, when it strikes the ground below, it's moving at 53 meters per second. We want to find the height of the cliff. Right? So we're dealing with a situation like this. Here's the cliff. We do not know how tall it is. What we do know is that when the car drives off, it's moving at 25 meters per second, and then it does this. Okay, and encounters the ground at a speed of 53 meters per second. We want to figure out the height of the cliff. Okay, so similar to what we just did, except this time we're solving for initial height instead of final. Okay, I'll give you a few minutes on that one. Okay, so once again, we have a situation where something is falling. So gravity is the only force acting on it. So thus, the mechanical energy when the car drives off the cliff is equal to the mechanical energy when the car crashes into the ground. Okay, the instant it hits the ground, not obviously after it's changed shape and made a crater and all that kind of stuff. Okay, so what we have here is a situation where we do have an initial kinetic energy because it is moving. We obviously have an initial potential energy because it's at the top of a cliff. Okay, and we have a final kinetic energy, but do we have any final potential? How high is the ground? 0. All right, so what we have is essentially this situation. Initial potential plus initial kinetic equals final kinetic. There isn't any final potential. All right, so we can eliminate that right off the bat. What we're looking for is part of this. It's part of the initial potential energy. So I want to get that by itself right away. So what do I have to do with the initial kinetic? Subtract it over to the other side, right? So I'm going to have the initial potential equals the final kinetic minus the initial kinetic. Okay, everybody with me so far? Okay, so we have m times g times h initial equals 1/2 mv final squared minus 1/2 mv initial squared. Again, the mass of the car isn't going to matter here because the final speed of the car is independent of its mass. Okay, so we are looking for hi. What do I have to move in order to get hi by itself? G. So I just divide both sides by g, and I've got hi by itself. So my initial height will be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Right, that should get me my initial height of the cliff. So 0.5 times 53 squared minus 0.5 times 25 squared, okay, divided by 9.81. All right, so we're looking at a cliff that's 111 meters high. Okay. Questions on that one? So really, guys, the only things you're going to ever be asked to calculate with a law of conservation of energy problem is a height or a speed. Okay? And the manipulation, whether it's initial or final, really isn't any different. So as long as you can do those manipulations, you can do these questions. Okay? The understanding parts of these things is reading the context of the question, being able to decide, am I looking for an initial or a final? What do I have? Are any of them zero? Okay, that kind of thing. That's what kind of takes the practice. Okay, so different situation here. Skydiver jumps out of a plane moving at 90 meters per second, and they're 10,000 meters above the ground. How fast will the diver be falling when he is 8,000 meters above the ground, assuming he has not opened his chute? Okay, and why do I bother saying that? If he opens his parachute, will he fall at 9.81 meters per second squared? No. Okay, so that's why we say he hasn't opened the parachute. Otherwise, we don't know what G is. It would be something else, and that would really change things up. All right, so I want you guys to give this one a try. Okay, we're looking this time for one of the two speeds. Okay, so I'll give you a little bit of time on that. All right, what we do know is we know our initial speed, 90 meters per second. We know our initial height, 10,000 meters. Okay, and we know our final height, 8,000 meters. Okay, so if you jump out of a plane, do you have mechanical energy? Yes, that's the problem with jumping out of a perfectly good plane, is that you have a lot of mechanical energy, okay? And you have the potential to do a lot of work on the ground when you hit it, so, okay, that can be bad. We've got our initial mechanical energy is going to be equal to the final mechanical energy. Okay, that's not going to change because this is a person who's falling in an isolated system. Obviously, we do have initial potential energy because we're 10,000 meters above the ground. We also have initial kinetic energy because we jumped out of an airplane moving at 90 meters per second. Okay, and we have final potential energy because we're 8,000 meters above the ground. That also means we have final kinetic because we're lower than we were before. All right, so we have all four kinds. Okay, none of these are zero in this example. All right, what we're looking for is part of our final kinetic because they want to know how fast he's going at the 8,000 meter mark. All right, so I'm going to subtract the potential final over to this side. So I'll have EP initial plus EK initial minus EP final equals EK final. All right, so that's my first step. Now I can plug in all of my formulas. All right, so I'll have M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. Mass is going to cancel because, again, I'm being asked to solve for a speed or a height. Those are independent of mass. Okay, and I want to get VF by itself. So what do I have to do to this 1/2? Divide it over to the other side. Okay, and I'm looking for VF, not VF squared. So I need to square root. Right, now I'm solving for VF. So when I plug in my numbers, I'm going to have 9.81 times 10,000, my initial height, plus 1/2 times 90, my initial speed, squared, minus 9.81 times 8,000, my final height, divided by 1/2. Right, that should give me my final speed, which is going to be pretty fast. Right, it's falling 2 kilometers. Okay, it's a long way to fall. You're going to pick up a lot of speed when you do that. Okay, so we'll have 9.81 times 10,000. Okay, plus 0.5 times 90 squared. All right, minus 9.81 times 8,000. Okay, divided by 1/2, square rooted. All right, so he would be falling at 217.6 meters per second. That's fast. Yeah, okay. Every 5 seconds, you fall a kilometer, right? But actually, it would be picking up speed, so it would be even more than that, which would mean that eventually he would break the sound barrier, right? And that's a problem because breaking the sound barrier is really hard on things. Okay, it took years of smashing and blowing up planes in order to figure out exactly how you pass through the sound barrier, right? A person would require a special suit, okay, in order to do that.
So if this is an isolated system, why is it important to leave it in?
Well, it isn't. In an isolated system, the parachute would do nothing, right? So if we were in that vacuum chamber that we watched that video about, and you jumped and you pulled the parachute would do nothing because it wouldn't fill with air, right? So yeah. All right, I'm going to give you guys about a 5-minute break here because we've been working on those pretty steady since the beginning of class here. So I'll give you a 5-minute break, and then we'll look at something else here. Okay, so if we're looking at number 15 here, the big thing with number 15 is that we have to have this understanding that the mechanical energy doesn't change at any point on the way down, and that kinetic and potential always add up to mechanical, and it's going to be the same number, right? So all I have to do is calculate the mechanical energy one time. And the easiest place to do that is the initial point where it has no kinetic, it's all potential, right? So initially then, I'm just going to calculate the potential energy at a height of 20 meters. So it was a 2 kilogram mass times 9.81 times 20 meters. Okay, so my mechanical energy is 392.4 joules. And I can write that in every single box all the way down, because that number never changes. That's what the law of conservation of mechanical energy says, okay? That the mechanical energy will be conserved and not change all the way down, right? Now, that means also at this first point that this number here is 392.4 joules, and this number is 0. All right. So do I ever actually have to use 1/2 mv squared at all in this question? Nope. Okay. I don't need to know the speeds. I don't need to calculate them. Okay. All I need to do is calculate the potential energy at every height, and then I calculate EK by doing what? Subtracting it from the mechanical energy. All right. So we'll have 2 times 9.81 times 15. All right. So 294.3. joules, okay, 2 times 9.81 times 10, right, which is 196.2 joules, okay, and then at 0 meters, obviously it'll be 0 joules, and this number here will be 392.4 joules. And then to find these other two, I just do my subtraction operation. So 392.4 minus 294.3. So my kinetic energy here is 98.1. Okay, and the second one, it's 392.4 minus 196.2, which I think is 196.2, isn't it? Yeah. Okay, that's all I have to do to fill in that chart. All that question is trying to do is remind you, here's how you calculate mechanical energy. Remember that mechanical energy is the sum of potential and kinetic, and that it doesn't change as an object falls. Okay, that's going to be the big thing. How many people have done all 4 of those? Okay. So I have one more that I want you to work on here, okay, that's in my mind kind of important, and that is going to be, okay, I want you to try 5 and 6 here from these kinetic energy problems, okay, because they have to do with kind of work energy theorem as well. So I'd like you to try 5 and 6, and then we'll probably leave it at that. Reminder, tomorrow your work labs are due. So make sure you have them done and submitted on Google Classroom for the start of class. Okay, remember that your unit exam is coming up next week. I'm going to post the review package right now. Okay, so you'll have that to look over the weekend. Okay, and that would be a good idea. And then next week you can come in and see me for help if you have any questions. Right? I will probably do the unit exam review. I think I was thinking of doing that on either Friday or Monday. So we'll see where we're at.